Welcome to solution composition. So we often use the qualitative terms dilute and concentrated to discuss the concentration of a solute. So dilute means relatively little of our solute is present, and concentrated means relatively large amounts of our solute are present. But we need a more quantitative way of measuring our concentration. So we have a few different ways of measuring concentration. We have molarity, mass percent, mole fraction, molality, and normality. So first let's look at molarity. So molarity is equal to the moles of solute divided by the liters of solution. So if we have 1.00 grams of ethanol mixed with 100 grams of water to give us a final volume of 101 milliliters, well, we know we want moles of solute divided by liters of solution. We have milliliters of solution, so we can convert to liters. But we don't know yet the moles of our solute. We have grams of our solute. We have 1.00 grams of ethanol. Well, we can divide by the molar mass of ethanol, 46.07 grams per mole, and that will give us moles of ethanol. And then we divide by liters of solution. Well, we have 101 milliliters. Convert that into liters, and that gives us a concentration here of 0.215 molar. But we also have mass percent. So mass percent is equal to the mass of the solute divided by the mass of the solution times 100%. So we have our same case, 1.00 grams of ethanol mixed with 100 grams of water to give a final volume of 101 milliliters. In this case, the volume we don't care about. We know that the mass of our solute is 1 gram, 1.00 gram of ethanol, divided by the mass of the solution. Well, the solution is made up of water, that 100 grams of water, plus the 1.00 gram of ethanol. So that gives us 101 grams of ethanol. So multiply by 100%, that gives us 0.990% of ethanol in our solution. The next one is mole fraction. Mole fraction of some component A is equal to chi A, and this is number of moles of A divided by the total number of moles in our mixture. So total number of moles is the number of moles of A plus the number of moles of B plus the number of moles of C, and so on until you run out of components in your mixture. So if we have our same example as before, 1.00 grams of ethanol is mixed with 100 grams of water to give us a final volume of 101 milliliters. Well, we know that chi ethanol, our mole fraction of ethanol, is equal to the number of moles of ethanol divided by the total number of moles. So number of moles of ethanol is 1.00 grams of ethanol divided by the molar mass. And the total number of moles is the number of moles of water plus the number of moles of ethanol. So number of moles of ethanol is the same calculation as we have on the top, 1.00 grams of ethanol divided by the molar mass of ethanol, 46.07 grams per mole. And the moles of water is 100 grams of water divided by the molar mass of water, 18 grams per mole. And that then gives us the top, the numerator, gives us 2.17 times 10 to the minus 2 moles of ethanol. The bottom, the denominator, gives us 5.58 moles of water plus 2.17 times 10 to the minus 2 moles of ethanol, the same as what we had on the numerator. So that gives us a mole fraction of 0.00389 for the mole fraction of ethanol. So you can see that most of our solution is water, and that's not surprising because we had 100 grams of water for 1 gram of ethanol, but because the water has a smaller molar mass than ethanol does, the mole fraction is even smaller than the mass percent was. So now let's look at molality. This is not molarity, but molality. So molality is the number of moles of our solute divided by kilograms of solvent. So note here that this is different than molarity because molarity was moles of solute divided by liters of solution. In this case, we have moles of solute divided by kilograms of solvent, not kilograms of solution. So we have 1.00 grams of ethanol being mixed with 100 grams of water to give us a final volume of 101 milliliters. Again, we don't care about the volume. now have 1.00 grams of ethanol. We need to divide by the molar mass to give us moles of ethanol. And now we're going to divide by our kilograms of our solvent. We don't know kilograms yet, but we have our mass of water in grams. So 100 grams we need to convert to kilograms. And that then gives us a molality of 0.217 molal. So note here that molality is denoted with a lowercase m, whereas molarity was an uppercase m. So you need to be very careful when you're writing concentrations in molarity or molality, whether you're using an uppercase m for molarity or a lowercase m for molality. One more thing I want to point out here with molality, note that the molarity was 0.215 molar. So the molarity and the molality are not exactly the same. But as long as the solution is relatively dilute, the molarity and the molality will be approximately the same if the solvent is water. And that's because 1 liter of solution, if it's dilute, most of that volume, almost all of it, is from water. 1 liter's worth of water is 1 kilogram of water, and that means that the denominator in both cases will be almost the same. The numerator is the same because you have mole of solute in both cases, but that's not true for other solvents. So only in the case of water and only in the case of a dilute solution. If you have a very concentrated solution, then 1 kilogram of water added to your solute will give more, significantly more than 1 liter's worth of solution. All right, so normality is the number of equivalents per liter of solution, where equivalence depends on the reaction that's taking place. So for an acid-base reaction, the equivalent is the mass of acid or base that can donate or accept 1 mole of protons. So if you have an acid that is only monoprotic, it only donates 1 mole's worth of protons for every mole of the acid, then the normality and the molarity will be the same because it's equivalents per liter of solution. So if an equivalent is 1 mole of your acid, then equivalence per liter of solution is the same as mole of acid per liter of solution. On the other hand, if you have a polyprotic acid, let's say something that's like sulfuric acid, H2SO4, that has 2 protons it can donate. So there, for every 1 mole of sulfuric acid, you have 2 equivalents. And that means that the normality will be double the molarity in the case of sulfuric acid. So for a redox reaction, an equivalent is the mass of oxidizing agent or reducing agent that can accept or donate 1 mole of electrons. So again, if you have an oxidizing or reducing agent that is exchanging 1 electron for each molecule, or 1 moles of electrons for each mole of molecules, then the normality and the molarity are the same. But if you have something that is exchanging, say, 4 electrons per molecule, then the normality will be 4 times the molarity. So that was solution composition.